Hey, Ace-Trig students. Hope we're all doing well. Mr. Meunier back again. Today, I just want to do a brief overview intro of polar complex numbers. Polar numbers are new polar numbers based on radiuses and angles, but complex meaning we can have some imaginary forms. Quick reminder about a complex number from your previous algebra courses. Complex number simply means that we have a real piece and an imaginary piece. So 3 plus 4i would be considered a complex number because the 3 is real and the 4i is imaginary. So any pair of those is a complex. Plain old 3 by itself, again, that's real, 4i is imaginary. When they're together like this, it's a complex number. We tend to put the real part first and the imaginary part second. So 2 minus 3i would be a complex number. Real number of 2, negative 3i, imaginary. We can plot complex numbers on what's called the complex plane. When we do this, the form we go in, the accepted form would be the real axis, kind of takes the place of our traditional x-axis, and the imaginary axis takes the place of our typical y-axis. So real number first, imaginary number second. Real is like the x, imaginary is like the y. That's kind of why we go real then imaginary, x comma y for a traditional point. So we have a real axis and an imaginary axis. So how do I plot this? Just like you would plot any rectangular point, because again, in this form, we're basically saying this real number is an x and the imaginary number is a y. So instead of an x-axis, y-axis, though, traditionally, we should say this is a real axis and an imaginary axis. The real is a positive 3, the imaginary is a negative 2. So point Z, the complex number, is in this location provided, 3, negative 2i. We don't say this is not 3 comma negative 2. That means we have a real normal point on the real rectangular grid system. This, with the real and imaginary axis, corresponds to a complex plane. Right? So again, that's how we plot a point in complex. Now, the magnitude or the modulus of a complex number is simply its distance from the origin. So we might be asked to find the magnitude or the modulus of a complex number. That's the distance it has from the origin. We can get that by the same way we find the magnitude of a vector or the radius of a polar point. It's just radical x squared plus y squared, where again, x corresponds to real and y corresponds to imaginary. We tend to use an absolute value symbol to denote that we want to find the modulus of that complex number. So graph each number in the complex plane and find its modulus. We have 3 plus 2i, and again, that's kind of like an x and a y in our sense. We can plot this. Real axis, imaginary axis. Real is 3, imaginary is 2. So point Z is in that location. Its modulus then is how far it is from the origin. That dotted line would be considered the modulus. And we can find that just like we found other items as kind of a spin on the Pythagorean theorem. The modulus of Z would be radical 3 squared plus 2 squared, which is radical 9 plus 4, which is radical 13. Or that would be 3.5-ish as a decimal. Here, again, this is technically not a complex number. It's an imaginary number, but we can still plot it on this complex plane. just realize there's a 0 real number for I imaginary number. So you have the real axis, imaginary axis, 0x, 4 for the y. Our points on the y-axis there are the imaginary axis. Its modulus is the distance to the origin. So we can kind of count that one here and see it's a 4. Or again, our formula still works. It's 0 squared plus 4 squared, which is going to be 0 plus 16, which is going to be a 4. All right. So previously, with normal polar numbers, we talked about converting things back and forth. And we had, for instance, we always knew that the x coordinate rectangular corresponded to r times the cosine of theta, polar. The y coordinate rectangular corresponds to r sine theta, polar. So if we have a complex number where the real piece is considered to be x and the imaginary piece is considered to be y, we can substitute things in. X then would be replaced by r cosine of theta. Y is replaced by r sine of theta. So r cosine theta plus r sine theta I, because again, y is the imaginary piece of a complex number. Both of these items have r in common. So if I factor the r out, we have this setup, r times cosine theta plus I sine theta. This is polar complex. Or again, this beginning x plus yi is rectangular complex. Okay. Get rid of that. So here, we want to write the polar, the rectangular number in polar form. So this is not a real number. -3 plus 4i. This is a rectangular complex number. To make this happen, I need to know what is the radius and what is the angle. So I need radius and angle. We should know from before the radius is always radical x squared plus y squared, and the angle is always the inverse tangent of y over x. If we begin to work this out, the radius is going to be radical -3 squared plus 4 squared. That's going to give us a 5, while the angle is inverse tangent of y over x. Sorry. In this case, it's going to be 4 over -3. And notice, since the x value is negative, we do need to add 180. Whenever x is negative, you have to add 180 to your angle. Let's go ahead and do this one in degrees. So if I do the inverse tangent of 4 divided by -3, and I add 180, and I'm doing this one in degrees, we're going to get 126.9 degrees. Okay. So what this answer is not, do not write this as 5, 126.9. No. That represents a point in the real polar plane. This is an imaginary polar number. It was an imaginary number at the beginning. So it needs to take the form up above in this green box of 5, then the cosine of our 126.9 degree angle plus I sine of our 126.9 degree angle. This is polar complex. That is polar complex. Now, there is a shorthand method of writing this that I will accept. instead of writing all of this out, you will say shortcut is RCIS theta, the radius, cosine, I sine, angle. So in this case, it would be 5 CIS 126.9. Okay. And that's how we would go about working these out. So I did that one in degrees. I'll go and do this one in radians. If it says specifically one way or the other, make sure to follow that. If not, it's kind of a your choice thing. It depends on the problem you're doing. So here we have our rectangular complex number. The radius of this is radical 1 squared plus radical 3 squared, which is going to be radical 1 plus 3, which is a 2. Our angle is the inverse tangent of radical 3 over 1. I don't need to add 180, or for this particular problem, pi. Since we're in radians, I want to add pi, but I don't because it's a positive x value. The inverse tangent of radical 3 is pi over 3. So we can write this 2 the long way times cosine pi over 3 plus I sine pi over 3, or the shorthand method of 2 CIS pi over 3. Do not put 2 comma pi over 3. That is a real polar number. We want a complex polar number. All right. And then we can also go the other direction. So we have a point, a polar complex point of -3 cosine 60 degrees plus I sine 60 degrees. Plot this in the complex plane. So again, here's 0, 15, 30, 45, 60. I have a 60-degree angle. Move towards that, but the radius is a -3. That tells me to go away from that angle. So into the third quadrant, third ring puts Z in the location where I put that dot. But then change this to rectangular form. Well, I got to know that X is always our cosine of theta and Y is our sine of theta. So in this case, X is -3, cosine of 60 degrees, Y is -3, sine of 60 degrees. -3, the cosine of 60 is 1/2. -3 sine of 60 is radical 3 over 2. We get -3/2 for X, -3 radical 3 over 2 for our Y value. And like above, do not write this as an ordered pair. That means a point on the real rectangular grid. This is a complex number where X does represent the real piece of it, -3/2, and Y represents the imaginary piece of it. So -3/2 minus 3 radical 3 over 2I. All right, so again, that's complex number, a polar complex number, and working back and forth between those two. Now I'm going to quickly transition to the next page of notes on how we multiply and divide these polar complex numbers. So again, let's flip this to the next page, multiply and divide. Typically, we would go through the proof on this, but with time being what it is, we're going to kind of cut to the chase. If you're going to multiply two complex polar numbers, the shortcut comes down to you multiply the radius and you add the angles. That's it. Multiply the radius, add the angles. Multiply the radius, add the angles. So find the product of -4 cosine 20 plus I sine, or -4 cosine 200 plus I sine 200 times 6 cosine 185 plus I sine 185 then put this in rectangular form. So the product would be -4 times 6. Radius you multiply. I'm going to do the shorthand method here. CIS, 200 degrees plus 185 degrees. That's a -24. CIS, 385 degrees. We tend to want our angles to be between 0 and 360 or 0 and 2 pi. So I can subtract 360 and get 25 degrees. That's our polar complex number. To put this in rectangular form, I need x to be -24 cosine of 25 degrees, and y is -24 sine of 25 degrees. 25 is not something we would know, so we have to go to our calculator. -24, oopsie. Cosine of 25. Oops, Control Enter. And -24 sine of 25. We get -21.8, -10.1. Don't write that as an ordered pair. X is the real number minus 10.1 is the imaginary. -21.8 minus 10.1i. So this is polar complex. This is rectangular complex. So two things, multiply the radius, add the angles. Multiply the radius, add the angles if you have polar complex numbers. And finally, if you want to divide polar complex numbers, the shortcut, cutting to the chase, would be divide the radius and subtract the angles. Divide the radius, subtract the angles. Divide the radius, subtract the angles. So find the quotient. 4 cosine 60 degrees plus I sine 60 degrees divided by 10 cosine 90 degrees plus I sine 90 degrees. This would be 4 divided by 10. Divide the radiuses. CIS is the shorthand way for polar complex of 60 degrees minus 90 degrees. Go left to right, like reading a book. So that would be 2/5 CIS, -30 degrees. We tend again to want to be between 0 and 360. So I can add 360 to that and get 330 degrees. So that would be a polar complex. Putting this in rectangular form would be 2/5 cosine 330, and y is 2/5 sine of 330. So that's 2/5. Cosine of 330 is radical 3/2. 2/5. The sine of 330 is -1/2. Which gives us an x of 2 radical 3/10 and a y value of -1/5. Actually, that would not be, that would reduce down to radical 3/5. 2's cancel. Do not write this as an ordered pair. This is an imaginary complex number. So the real piece is radical 3/5 minus the imaginary piece is 1/5 I. All right, guys. Hope we're doing well. All right. So see you later.